Well, so in part two, chapter number 7, part two, we're going to discuss two things, and that's a little bit long discussion in with respect to cost in the short run and cost in the long run. Because as you mentioned, as you know, we discussed in the part one that in the short run, all the factors of productions are not variable. Some are fixed. So it means that there is a cost is fixed for that factor of production. But in the long run, all factors of production are variable. So it means that cost is going to be variable over the long period. All the costs are variable in the long period of time. So that's a main idea. In this part, we're going to discuss cost in the short run and cost in the long run. So the shape of the cost curves, from your micro principles of micro. So costs are basically a vertical summing up. Like when there is a fixed cost, there is a variable cost. So when you sum up this fixed cost plus variable cost, that is going to be the total cost. So we see here these three curves. Like this is a fixed cost curve as it is fixed. So keep it in mind that we are talking about short run. So this is our fixed cost. This is our variable cost. So when we plus this, so we get a total cost. So in panel A, so total cost is a vertical sum of fixed cost and variable cost. So you see here the fixed cost is starting from this, total cost is starting from this point. Why? Because the fixed cost is there. Variable cost is starting from zero. It's not uh, or from origin. Total cost is not starting from there. Total cost is starting from the fixed cost. So in the B, average total cost (ATC) is the sum of average variable cost and the average fixed cost. So we also see here that this is our fixed cost curve, this one, average fixed cost curve, and this is our average variable cost. And when we sum up, we get it average total cost curve. So marginal cost curve crosses the average variable cost and average total cost curve at their minimum. So that's a very important property of marginal cost curve, is that marginal cost curve is crossing or intersecting the average variable cost and average total cost. So if that's the case, we can say that the average total cost and average variable cost is minimum when it is equal to marginal cost, right? It is minimum because they are crossing from this point. So it's important to note. The average margin relationship, that's what we discuss here. What is the relationship between average variable, average fixed cost with the marginal cost? So marginal and average costs are another examples of an average margin relationship described in chapter 6, what we discussed with respect to margin and average product. Because average total cost is a sum of a average variable cost and average fixed cost, and the average fixed cost declines everywhere, so the vertical distance between ATC and AVC curves decreases as output increases. So what we are explaining here, that average fixed cost in a short run is always declining, always, because as we are producing more and more, the average fixed cost is decreasing. So we see that average variable cost and average fixed cost, average total cost are quite apart in the beginning when we are producing less units. But as we are producing more and more units, they are getting closer and closer. They are getting closer and closer, right? So their distance or their difference become less and less. Why? Because the average fixed cost is decreasing. Total cost as a flow concept. Total cost is a flow. The firm produces a certain number of units per year. Thus, its total cost is a flow. For example, some numbers of dollars per year. For simplicity, we will often drop the time reference and refer to total cost in dollars and output in units. So it's a flow concept. We are talking about certain particular time period, and we always calculate on the basis of total cost per year, total cost per month, or total cost per week, or whatever the time frame we are using. But normally when we are in our discussion or in our explanation, we drop the time frame out of it. We just talk about total cost, but it should be of a certain time period. So knowledge of a short-run cost is a particularly important for firms that operate in an environment in which demand conditions fluctuate considerably. If the firm is currently producing at a level of output at which the marginal cost is sharply increasing and its demands may increase in the future, management might want to expand production capacity to avoid higher costs. Now, here is an example the firm is facing to decide the production of aluminium. Aluminum begins with the mining of bauxite. The process used to separate the oxygen atom from aluminum oxide molecules, called smelting, is the most costly step in producing aluminum. The expenditure on smelting plant, although substantial, is a sunk cost and cannot be ignored. Fixed costs are relatively small and can also be ignored. So these are the costs. Like, now, what is important to note here is there is a capacity, and that's what we call it as a short run. And if we want to go over and above capacity, then this is the situation. Electricity is consumption is same whether we are producing this much or more. Aluminum is the same. Other raw materials, plant, power and fuel, and substantial subtotal, we get at this. Now, but if per ton, that increase when output exceeds 600 tons. So if we are in between 600, so labor cost is increased if we go over and above the 600. The maintenance cost increase, the freight increase, the by this way the subtotal increase. Now you see these costs are same, but these costs change when we increase the capacity. When we increase the capacity or when we run the plant for 3 shifts. For an output which Q up to 600 per ton, the total variable cost is 1140, what we calculated here, 1140. So marginal cost and average cost are constant at 1140 per ton. This is per ton, that's why we call it as a marginal cost and the average. If we increase production beyond 600 tons per day by means of a third shift, the marginal cost of labor, maintenance, and freight increase from 320 to 480. So these 320 to 480 per ton, which cause marginal cost as a whole to increase from 1140 per ton to 1300 per ton. So that's an increase or a jump if we are producing more than 600. So if we want to write a formula for this situation, we are saying if we are producing 600 tons, that is our marginal cost into 600 plus 1300 into Q minus 600. So up till 600, this is the cost. Whatever we are producing, like we are producing 605. So 605 minus 600 means 5 more. And 5 is going to multiply with this new marginal cost. And by this way, we simplify it and we get this. Now, what is this? This is our total variable cost equation. And when we divide it with the Q to get an average variable cost, so this Q is eliminated, it's going to be 1300 as it is, and 96,000 divided by Q. And we can see in this figure that the short-run variable cost of aluminium smelting, the short-run average variable cost of smelting is constant for output level using up to the labor shift. When a third shift is added, marginal cost is and average variable cost increase until maximum capacity is achieved. So you see here, it's a jump from 1140 to 1300. Although this is going to be moved like this if we are producing up till the 900. The user of a cost of a capital, now there is a concept of a cost of a capital. In the long run, we are adding up the cost of a capital as well, because in the long run, if we want to increase the capacity, then we have to look at like, okay, if we can change the capital, then how much is the cost. User cost of capital, annual cost of owning and using a capital asset equal to the economic depreciation plus foregone interest. So these all things we have to add up. The user cost of a capital is given by the sum of the economic depreciation and the interest that could have been earned had the money been invested elsewhere. So formally, we can say user cost of capital is a economic depreciation plus uh, interest rate into value of capital. So we can also express the user cost of capital as a rate per dollar of a capital. R, we representing here R in terms of a dollars, user cost of capital, depreciation rate plus interest rate. Now the cost minimization input choices. Now this is the way that we have to select now between capital and the labor, that how much we have to use capital and how much we have to use labor. So we now turn to the fundamental problem that all firms face: how to select input to produce a given output at a minimum cost. Cost minimization. For simplicity, we will work with two variable inputs: labor, measured in hours of work per year, and capital, measured in hours of use of machinery per year. So the price of a capital, in the long run, the firms can adjust the amount of capital it uses. The firm must decide prospectively how much capital to obtain. So in order to compare the company's expenditure on capital with its ongoing cost of labor, we want to express the capital expenditure as flow, so in dollars per year. So to do this, we must amortize the expenditure by spending it over the life of the capital, and we must also account for the foregone interest that the firms could have earned by investing the money elsewhere. So the price of a capital is its user cost, which given by R, and R is a sum of depreciation plus interest foregone. Now this R, the rental rate of capital, the rental rate cost per year of renting 1 unit of capital. So if the capital market is competitive, the rental should be equal to the user's cost R. And why? Because of the competition, they have to bring it down the price to the marginal cost. So that's why that's a competitive market. So firms that own capital expect to earn a competitive returns when and they rent it. So this competitive return is the user cost of capital. So capital that is purchased can be treated as now it were the rented or a rental rate equal to the user cost of. So it is we treat it as a same like a rented or a purchased. Now what we are doing here, we are building up a very similar like the concept what we discussed as a budget. So but here we are saying it's a cost line graph showing all possible combinations of labor and capital that can be purchased for a given total cost. So to see what an ISO cost line looks like, recall that the total cost of producing any particular output is given by the sum of the firm's labor cost. This is the wages into the labor, and the capital cost, which is R, rental use of capital, a rate of this, and K is the amount of capital what we are using. So we can write it, the cost is a sum of a WL plus RK. So if we rewrite the total cost equation as an equation of a straight line, so we can write it like K is equal to CR over C over R minus WR over L. So it follows that the ISO cost line has a slope of a delta K over delta L, or we can write it is like a minus W over R, like this is the slope. So if you look at this equation, we can get it also that this is the slope of the equation and this is the intercept of the graph. So which is the ratio of the wage rate to the rental cost of capital. Now here we are combining two things. One is ISO quant, what we discussed in chapter 6, and ISO cost, what we just discussed here. So producing a given output at a minimum cost. So ISO cost curves describes the combination of inputs to production that cost the same amount to the firm. So these are our different ISO cost curves. This level of total cost, providing all the combinations of all the combinations of labor and capital, and this level of cost provide all the combinations of capital and labor. So ISO cost C1 is tangent to the ISO quant Q1. So this is our ISO quant. So by this way we select that for this level of output, this much labor, this much capital, this much labor we have to use to minimize the cost. And where it is, where the slope of the ISO quant is equal to the slope of the ISO cost. Now please remember, this is our ISO quant which we discussed in chapter 6. This is our ISO cost we just discussed. Now what we are saying that the combination which is cost minimization, cost minimized combination of labor and capital is a point where the cost curve is tangent to the ISO quant curve, and ISO quant curve is the level of production. So for that level of production, you see here, it's the same concept what we discussed in our consumer theory. Like consumer is going to maximize the utility where their indifference curve, level of satisfaction, is tangent to their budget line, right? So that's a very same concept. Cost in the long run, input substitution when an input price change. So if any input is going to be expensive, so the budget, this cost line going to change. Like in this case, if you look, this is our C1 and this is our C2. Now if you look at very carefully, we can say that which is going to be expensive and which is going to be cheaper relatively. So we can say that I think the labor price is increasing, and that's why the line is going to be moves in, tilted in. So facing an ISO cost curve C1, the firm produce output Q1 at a point A using L1 units of labor and K1 units of capital. When the price of labor increases, that's what I explained you with this shift, this rotation. And the ISO cost curves become steeper, and output Q1 is now produced at a point B. Now this is going to be the tangent point. Now this point is no more being a tangent point for this new ISO cost line. So now this combination K2 and L2 is the new combination of asset, capital and labor. So cost in the long run, recall that our analysis of production technology, we showed that the magnitude of technical substitution. You remember the slope of the indifference curve, we call it as MRS, minor rate of substitution. But here in this case, for ISO quant, and we learn also in chapter number 6, the slope of the ISO quant curves are called as a marginal rate of technical substitution, MRTS. So we show that the minor rate of technical substitution of labor for capital, MRTS, is the negative of the slope of the ISO quant and is equal to the ratio of the minor product of labor and capital. So we see MRTS, minor rate of technical substitution, the slope is minus delta K over delta L. Or we can write it in this way, like MPL over MPK. Now, when we also know that it follows that when a firm minimizes the cost of producing a particular output, the following condition holds, which is MPL over MPK, and we see it is W over R. So, or we can rewrite that MPL over W or MPK over R, just to explain you or try to relate it with the consumption theory. You remember we discussed marginal utility of X divided by price of X should be equal to marginal utility of Y divided by the price of Y. So what we are finding here, this is the marginal product of labor divided by the price of labor, which is in wages. Marginal product of capital divided by R, which is the price of the capital or the rent of use of a capital. So it's the same thing, but here we are using in a different way. So cost minimization with varying output levels. So expansion path curve, like we will discuss here. This is an expansion path curve. Expansion path curve passing through points of tangency between firms' ISO cost lines and its ISO cost. So a different level of outputs with a different cost, ISO cost lines. So we can see points which are like this. You see here, these points. So these are all different levels of output and their costs, and we get a that's what we call it as an expansion path. Curves passing through a point of tangency between a firm's ISO cost lines and its ISO costs. The firm can hire labor at a wage rate of $10 per hour. So it's we are imagining here. Sorry. And rent a unit of a capital with R is 20 per hour. So given these inputs cost, we have drawn three of the firm's ISO cost lines. Each cost line is given by the following equation. C is equal to W is 10, so we 10 into L plus 20 into K. So we can say delta K over delta L, 50 minus 25. The path, the expansion path is a straight line with a slope equal to half. So that's a slope of the expansion path slope you see here. So when we are moving from this point to this point, so you see here 25 and 50, and then we move on to this point 50 and 100, and that's what we're using here. So here capital is 50 at 25 and the labor is 50. So when we move to the next tangency point, so capital is 50 and labor is 100. So what we did here is 50 minus, this is a delta K, and this is divided by delta L. So we get it this, which is the slope of a expansion path. So if a corporation or a firm increase their production, so this is going to be the line of their use of capital and labor. So expansion path and a long run cost. So to move from the expansion path to the cost curve, we follow three steps. Choose an output level represented by an ISO con, then find the point of tangency of the ISO cost with an ISO cost line. From the chosen ISO cost line, determine the minimum cost of producing the output level that has been selected, and graph is here. We can see here this one. This is our ISO expansion path, and as expansion path means that you are increasing your capacity, so that's a long run total cost curve. We get it. So the firm's expansion path and a long run cost total cost curve. So in A, the expansion path from the origin through point A, B, and C illustrate the lowest cost combinations of labor and capital that can be used to produce each level of output in the long run when both inputs to production can be varied. So in panel B, what we show the corresponding long run cost curve from the origin through A point D, E, and F, measuring the least cost of producing each level of output. Now we are explaining this with an example, like there is a firm who is using capital and energy. Energy efficiency through capital substitution for labor. Greater energy efficiency can be achieved if capital is substituted by energy. So this is shown as a movement along the ISO quant Q1 from point A to B with a capital increase from K1 to K2 and energy decrease from E2 to E1 in leading to a shift in the ISO cost. So that's the same thing that what we discussed in our the first example of this tangency point. Now this can be shift, like this one is just a change in the cost of capital and cost of energy. But when the technologically things improved, and when they are improved, so it means that the technology make it possible that both the inputs going to be cheaper, or both inputs can be of a less expensive. So in that case, we see that technology change implies that the same output can be produced with a smaller amount of inputs. Here, the ISO count labeled Q1 shows the combination of energy and capital that yield output Q1. The tangency with the ISO cost line at C occurs when energy and capital combination E2 and K2. So because of a technical change, the ISO count shift inward, so the same amount of Q1 can now be produced with a less energy and less capital, in this case at point D with energy. So technological possibility that way. Now long run versus short run. So we see that short run versus long run. Short run is a combination or a tangency point between ISO cost and ISO count. And long run means that when the ISO cost curves shift, because in long run we have to change, all the costs are variable. So when the cost change, then which path of expansion we adopted. So this is a very good example to understand the difference. So when a firm operates in the short run, its cost of production may be minimized because of inflexibility in the use of a capital input. So output is initially at Q1. So we see here, this is our ISO quant curve. This is our ISO cost curve, right? And we get at this point of tangency. Agreed? Output is initially at Q1. So in the short run, output Q2 can be produced only by increasing labor. So in the short run, we can only, if we want to produce Q2, like there is a more demand, or there's a special order or something like this, that we want to produce more. So our ISO count curve shift to upward. Now, if this is an upward shift, and we know that in the short run, we cannot change the capital. So capital consumption is not going to change. So then what we have to do? We have to increase the labor. And when we increase the labor, we can produce Q2. And for that reason, we need a L3 labor, yeah, from 1 to L3, because capital is fixed. In the long run, the same output can be produced more cheaply by increasing. So this is a short run. And we see it is not cost minimizing. Why? Because it's not tangent to the ISO count curve, right? So what we can do, we can produce the same output at this point in the long run only, when we also make it possible to increase the use of capital, change of capital. So when the capital is increased as well as the labor is increased, so we get this combination. So in the long run, the ability to change the amount of capital allows the firm to reduce cost. The most important determinant of the shape of the long run average and marginal cost curve is the relationship between the scale of the firm's operation and the inputs that are required to minimize its cost. So long run average cost curve, or a curve relating average cost of production to output when all inputs including capital are available. Short run average cost curve, curve relating average cost of production to the output when the level of capital is fixed. So long run marginal cost curve, showing the change in long run total cost as output is increased incremental by 1 unit. Long run versus short run cost curve. So long run average and marginal cost curve. So you see here long run marginal cost curve and long run average cost curve. So when a firm is producing at a point at which the long run average cost curve is falling and the long run marginal cost curve is less than long run average cost curve. Conversely, when long run average cost curve is increasing, LMC is greater than LSC, so the two curves intersect at point A where the long run average cost curve is its minimum. So this is the point of a minimum. It's a very similar like what we discussed in the short term. Economies and diseconomies of scale, we know this is a concept like when we produce more and more, what is happening, the fixed cost, average fixed cost is decreasing, and by this way what happens that the total cost is decreasing. But a point will come that we see that the total cost is increasing, like if we start producing more than this point, so what is going to happen, the cost is going to be increased. As output increases, the average cost of producing that output is likely to decline as least to a point. So this can happen for the following reasons. Now, why the economies of scale happens? Like when we produce more, the firm operates on a larger scale. Workers can specialize in activities at which they are most productive. So the productivity increase because of a similar type of job the workers are doing repeatedly. Scale can provide flexibility by varying the combination of inputs utilized to produce the firm's output. Managers can organize the production process more effectively. The firm may be able to acquire some production inputs at lower cost because it is buying them in a large quantities and can therefore negotiating better prices. The mix of inputs might change with the scale of firm's operation if the managers take advantage of lower cost inputs. At some point, however, it is likely that the average cost of production will begin to increase with now this is the way that we are defining diseconomies of scale. So there are three reasons for that diseconomies of scale. At least in the short run, factory space and machinery may make it more difficult for our workers to do their jobs effectively. Managing a large firms may become more complex and inefficient as the number of tasks increases. The advantage of buying in bulk may have disappeared once certain quantities are reached. At some point, available supplies of key inputs may be limited, pushing that cost up. So these are the reasons of a diseconomies of scale. So economies of scale is situation in which output can be doubled for less than a doubling of the cost. Like if we increase the cost, the output is, if we want to double the output, the cost is not doubling, less than double. Diseconomies of scale is that when we situation in which the doubling of output requires more than double our cost. So a firm enjoys economies of scale when it can double its output for less than twice the cost. The terms economies of scale includes increasing returns to scale as a special case, but it is more general because it reflects input production that change as the firms change its level of production. Increasing return to scale, output more than double when the quantities of all inputs are doubled. And economies of scale, a doubling of output requires less than doubling of cost. So, a few more things. Longer economies of scale are often measured in terms of cost output elasticity, EC. Now we see here EC elasticity. Cost output elasticity is the percentage change in cost of production resulting from a 1% increase in output. So delta C over C divided by delta Q over Q. So that's a cost output elasticity. To see how cost output elasticity relates to our traditional measurement of cost, we can rewrite this equation as follows. So EC is equal to delta C over delta Q divided by C over Q, which is marginal cost over average cost. So clearly EC is equal to 1 when the marginal and average cost are equal, where the marginal cost is at its minimum. Average cost is at its minimum because they intersect the curves we discussed. In that case, cost is increasing proportionately with output and there are neither economies or diseconomies of scale. When there are economies of scale, when cost increase less than proportionately with output, marginal cost is less than average cost, both are declining, and EC is less than 1. Finally, when there are diseconomies of scale, marginal cost is greater than the average cost and the cost output elasticity is greater than 1. For practical example, we can see here the practical example, the effect of effluent fee on input choices. So we see that Tesla electric cars with a price of around 85,000 when they introduced their first car have been unaffordable for most people. However, in 2017, Tesla will be producing a new car, mass market car with a starting price of about 35,000. To achieve such a dramatic reduction in the price, the company will rely on a scale economies in battery production in its new 5 billion gigafactory in Nevada. Battery costs are expected to decrease by one third to about 250 per kilowatt hour of energy storage, and fall further as production rises. So Tesla's average cost of battery production, we see this is our average total cost curve of a Tesla battery production. The average battery production cost was about $400 per kilowatt hour in 2016. The battery for Tesla's cost Model 3 has 50 kilowatt per hour capacity, which is at 400 per kilowatt hours, applies a cost of 20,000 per battery. However, that cost can be reduced substantially by inducing batteries in a large volume, a number of volume production in the objectives of a Tesla's gigafactory. Last thing is that the long run average cost curve. The relationship between short run and long run average cost curve. So we see here this purple line is a long run average cost curve, and we see many short run average cost curves that is within the envelope of a long run average cost curve. So the long run average cost curve is the envelope of the short run average cost curves, like SAC1, this one, and this is SAC2, this is SAC3. So these are all short run average cost curves, and we see the marginal cost curves as well, short run marginal cost curves as well. With economies and diseconomies of scale, the minimum point of the short run average cost curves do not lie on the long run average cost curves. So although here we see that these are all on the long run average cost curve, but with the economies and diseconomies of scale, the minimum point of the short run average cost curves do not lie on the long run average. So this one is reflecting as not it's a normal, it's not economies and diseconomies of scale, but if it is economies and diseconomies of scale, so these points can be different. It can be lower, but it can be higher as well. So it can. So this is our part 3. Now the next 2 parts are shorter because in which we are just discussing more mathematical ideas. So stay tuned. Thank you.